Well, welcome everybody. This is our next gauge theory semi-virtual, and our semi-here person is Michael Hutchings, and we're pleased to have him take it away.
All right, thank you. Can you hear me? All right, so there was a kind of learning seminar on families of diffeomorphisms, and I volunteered to give a talk there, but got asked to speak here instead. But my talk is still in the spirit of a learning seminar, and I'm a student. Maybe some experts can straighten me out on some things. So what I want to talk about is one is sort of general construction of Floer homology of families. In a sort of prototypical Morse theoretic situation. And then I want to briefly discuss a couple of examples where this has been done in various kinds of Floer theory instead of Morse theory in the literature. And third, some speculation about possibly doing this in gauge theory for, well, my favorite kind of gauge theory is embedded contact homology, but should be a version of this for Cyber-Witten, Floer homology, other kinds of gauge theory. So there, the question in that case, well, I'm pretty sure you can do this if you do the technical work. The question is it interesting, and are there any applications of that? Okay, so the model case. So we have a smooth fiber bundle. And let's make these closed manifolds. And so I think of this as, this is just a family of manifolds parametrized by B. And then we have a family of functions on these manifolds, which in the present setting, we can just take to be as a generic smooth function on E. So really I'm thinking of this as a family of functions on the fibers. Okay. And I also have G is a generic fiber-wise metric. So for a generic point in the base, the function on the fiber is a Morse function. So at every point, every generic point in the base, we have a Morse complex on the fiber, whose homology is the homology of the fiber. And then the question is, what can you do with this whole family to get some invariant to the family of Morse functions? So one thing you can do is I'm also going to choose a generic connection, which allows me to relate different fibers to each other. And I'm going to choose an auxiliary Morse function on the base and GB is a metric on B. And then there's an associated gradient vector field. Let's denote this by W. So it's the gradient of FB with respect to GB. I'm not sure the best notation for that. So this is the gradient vector field on B. And I want to choose this function B such that assume that the Morse complex is defined on the fiber over each critical point of FB. So we can then set up a chain complex and it actually has a filtration on it. So the chain group is going to be a sum of chain group Cij, and Cij is the, well, it's generated, and we could use integer coefficients if we want, but I don't talk about signs in public, so we'll use CMA too. By pairs. XY, where X is an index I critical point on the base. And Y is an index J critical point on the fiber. So this is an index, so X is an index I critical point of FB, and Y is an index J critical point of the function on the fiber. So F restricted to, I should call this a name, this map is pi, pi inverse of X. So here's our total space E. Here's the base space B. So we have a critical point of FB. Over that, there's a fiber, and the function on the fiber has some critical points. So we pick one of these points and then one of those points. Okay, and then the differential counts flowing to the vector field V. So it's the sum of the fiber-wise gradient vector field. So this is I don't really know a good notation for this. So this is the fiber-wise gradient. Plus a component which moves in the direction of the base. So, so plus the horizontal lift of W. So, so if I have another generator, let's see. These are all white. Oh well. Well, this is orange. So if I want to look at the differential coefficient from here to here, I need to find a flow line from here to here, and then this gets lifted to a path here, which in the horizontal direction is lifting this flow line, and then the vertical derivative is the gradient flow line at the given fiber. Where's the eraser? There. Oh, these? Okay. So then the differential, so this looks a lot like, you can prove that d squared equals 0. This looks a lot like Morse theory, but that's an illusion because this is just the prototype. In the more interesting examples, you can still do Morse theory on the base, but then on the fibers, you're going to be doing some kind of Floer theory. So you can write the differential as d0 plus d1, et cetera, where di decreases the index on the base by I. So this is a filtered chain complex. So you can extract various information from it. Well, you could just take the homology of the whole thing, and if you do that, you're going to get the homology. In this case, just the homology of the total space. Similarly to the isomorphism between Morse homology and singular homology, you can also get a spectral sequence. And you can prove that this is isomorphic to the Leray-Serre spectral sequence of this vibration. More generally, you can think of it as a filtered chain homotopy type. So to get an idea of what's going on here, so we know that that D0 is just the fiber-wise Morse differential. So this counts flow lines which only go in the fiber direction and stay constant on the base. So then the homology of D0 in degree k, if you like, is the sum I plus j equals k. And the sum x is a critical point of index I of the force function on the base of hj of the fiber. And then, from that equation, d1 acts on the homology of d0. So this, that counts flow lines where this index on B goes down by 1, and then we lift it up to the base. And this gives you this gives you continuation map on Morse homology. So if you have a flow line in the base, you can use the parallel transport of the connection to identify the fibers over the two endpoints of that flow line. And then we know that Morse homology doesn't depend on the choice of Morse function and metric, and there's a continuation map that gives you an isomorphism. And that's exactly what this D1 is counting. So the homology of this, of D1 acting on D0 in degree K, is the sum I plus J equals K of HI of the base with coefficients in the local coefficient system given by HJ of the fibers. So it's just the E2 term of the Lie spectral sequence. And from there on, it's isomorphic to the Lie-Serre spectral sequence. So I wrote a paper about this a long time ago. And there's also an erratum on my webpage. I didn't say something quite right. So I wrote a paper called Floer Homology of Families 1. And I was going to write a part 2, except I couldn't think of any interesting applications of all this, so I never got around to it. Yes? Oh, the box. Can you toss in the box?
So V isn't the gradient of your original function, but if I took your original function, where was your function's gone now? The function on the total space, yeah. And I added a very large multiple of FB to it, then W's almost gradient-like for that guy. Kind of fails barely at the critical points, right?
Right, yes, if something very interesting happens if you do that. Yeah. I mean, you could take some limit to make in which it converges to an actual just Morse theory.
Sure. Yeah.
There's also some. If you do the opposite thing, I think, where you sort of move very slowly on the base, so you sort of multiply FB by a very small constant, you get. Well, at least that's the continuation maps. You get some picture where it follows critical points and then jumps when there are bifurcations. So you sort of see the at least I think that's what happens. So you see the bifurcation picture of continuation maps.
Yeah.
Right. So there are other ways you can do this. Like you don't really have to use Morse homology on the base. You can use singular homology. There are probably better homotopy theoretic ways to say all of this, which I'm not an expert in. But that's the finite dimensional model. Any other questions about that?
If you wanted to do the homework problem to see that this actually computes the homology of the total space, what's the slickest? I mean, assuming you know Morse homology computes the homology of.
Like I would imitate the proof. So I would say you look at the for any critical point in here, you look at the descending manifold with respect to this vector field W. I can't remember if that's stable or unstable manifold. Anyway, you look at that whole manifold, and you can then compactify it. It's actually a ball, but you don't really need that. So if you know it's a ball, you can say it gives you a CW complex structure on the whole space. If you don't know that, then you can just sort of triangulate this compactification to get a map from this this whole chain complex to the singular homology, similar to Morse homology.
Since we're doing questions, what happens if you just defined two separate boundary maps on the double complex corresponding to the Morse count in the base and then the Morse count in the fiber and then let C be a total complex for that? Do you get the same thing or?
Well, that would be something smaller because I'm looking at I'm looking at things where not only where the index difference on the base is 0 or 1, but it can also be bigger. And actually the index, in that case, the index on the fiber goes up. So like if you just looked at D0 and D1, I think you would just get the homology of the base with coefficient. You get the E2 term of the spectral sequence. But then there are these higher maps. So like if you have, you know, let's say this is index I minus 1, index I minus 2. You flow lines like this. So the D1 is counting things along these sort of index difference 1 flow lines. And then in the Morse homology of the base, there's a one-dimensional moduli space of flows going between these two broken flow lines. And D2 gives you some kind of chain homotopy between the composition of these two chain maps and the composition of those two chain maps, and so on. So the whole thing is built out of, you know, continuation maps and chain homotopies between them, and then homotopies of homotopies, and so forth. Yeah. Oh, you're in Zoom. Oh, there you are. Right. Apologies. Yeah. Right. Well, we could maybe we could do an example to clarify that. So, so let's say the base is the circle. And we have, let's choose the Morse function on the base with just one index 1 critical point. Let's call this y1, and sorry, x1. And one index 0 critical point, let's call this x0. So you might think that D1 is equal to 0 because I have two flow lines which cancel out, and it's just a continuation isomorphism. But the thing is, if this is a non-trivial bundle, then these continuation maps are different because there's a monodromy of this map, of this bundle, which is some diffeomorphism up to isotopy of M. So if I want to compare the fibers over these two critical points, I have to parallel transport along one path or the other. But those parallel transports are going to differ by phi. So after you've chosen some one of these identifications, then D1 acting on H star of D0 is the identity minus the map on homology induced by phi. That's right. Okay. Great. Other questions? Okay. So This is great, because I was worried I wouldn't have enough to say, but it looks like we'll be fine. So some Floer theoretic versions of this. So, of course, any version of Floer theory has its own complications, and so you have to sort of interpret and do some work to make sense of this in any kind of Floer theory. But one useful application of this approach is in equivariant Floer theory. So among other things, there's a paper by Seidel and Smith which constructs Z2 equivariant Lagrangian Floer theory. When you have a symplectic involution, and there's the work of, well, you can do this construction in their setting, although I think they actually needed a different version. And then there's a work by Bourgeois and Awancha defining S1 equivariant symplectic homology. I can just say briefly what this looks like. So first of all, so back in the finite dimensional version, so in the finite dimensional model, if you have an S1 action on a smooth manifold M, then you can make the homotopy quotient. So you take M cross ES1 modulo S1. This maps to BS1 with fiber M. So in BS1, this is CP infinity. And you can sort of think of this as a direct limit of doing this over CPn as n goes to infinity. So when you have this bundle over CPn, you've got a nice bundle with fiber M, and you can do exactly this construction. So you do the previous construction over CPn, and you take the limit as n goes to infinity, and this recovers the equivariant, S1 equivariant homology of M.
I will relay a comment from, I think, Hiro. He was commenting that a different way to think about John's question is that group homology is interesting in many cases, and the complex that you're computing is the group homology of the based loop space of B in coefficients generated as the Morse complex of the fiber.
Yeah, okay.
Yeah, okay. Thanks, Hiro.
Maybe we can discuss later and I can clarify. So what Bourgeois and Awancha did is we looked at, so X is a compact symplectic manifold with contact type boundary. So it looks like this. It has some boundary Y. And then the usual thing you do in symplectic geometry is you do a so-called completion. So denote by X hat, which is X union along Y of 0 infinity cross Y. So you can actually put a symplectic structure on this. And then symplectic homology is the homology, the Hamiltonian Floer homology of this completion with respect to a suitable Hamiltonian H on this completion, which goes to infinity as you go up the ends. So it's generated by, I guess I should have said that, sorry, H really also depends on S1. So it's generated by loops gamma from S1 to X hat, satisfying gamma prime of t is the Hamiltonian vector field of HT at gamma of t. And the differential counts holomorphic cylinders, or really there's solutions to perturbation of the holomorphic curve equation. So it maps U from R cross S1 to R cross X hat, and they satisfy the equation DSU. I forgot to tell you there's a J. So there's a family of almost complex structures, JT, parameterized by T and S1. So DSU plus JT of DTU minus XHT equals 0. And heuristically, you can think of this as some kind of infinite dimensional homology of the parameterized loop space of X hat. Now, this parameterized loop space has an S1 action which parameterizes the loops. So you could say, well, can we make some kind of S1 equivariant homology of loop space, which would be some kind of homology of unparameterized loops. So bourgeois nuances sort of start with this picture, and they sort of choose the data that depends on BS1 and ES1. So they choose So you choose JT, Z, HTZ, where T is in S1, and Z is in ES1. And these have to have a certain S1. You really want something defined on this quotient by S1, so it has to have a certain symmetry. And then they look at a parameterized version of this equation, analogous to the finite dimensional model we talked about before. So you choose FB from CP infinity to R, and there's a standard Morse function which you can use, which has one critical point of every non-negative even index. And you could also think of this as a direct limit of functions on CPN. And then they look at a chain complex. So you have X gamma, where X is a critical point of FB, and gamma is a one periodic orbit of the Hamiltonian for for a lift of X, modulo S1. So a lot of notation if I write the whole thing, so I'll just sort of give the rough idea. And the differential counts pairs A to U, where eta is a flow line of the Morse function on the base. And then you have a parameterized version of Floer's equation. So you have so we actually want to take eta tilde to be a lift to ES1, and then you have DSU plus JT eta tilde of T of DTU minus XH T eta tilde of T equals 0. And you have, there's an S1 action on the whole space of these, so you have to mod out by S1. So basically you take Floer's equation, but the data in the equation, the almost complex structure in the HT, now depend on where you are in the base in CP infinity. So you're coupling this flow line in the base of CP infinity to Floer's equation. So they can do all of that. And the reason why that's interesting, at least to me, so this is valuable because the resulting theory is rigorously defined So there's no, you don't need any sort of virtual stuff because since you, I guess I probably should have assumed that this is exact, so you don't have to worry about any bubbling. Since it's rigorously defined, and can be used as a ersatz, or replacement for linearized contact homology. So linearized contact homology is generated by Rabe orbits of the contact form. The differential should count holomorphic cylinders in R cross Y. And then you have to add some correction terms involving holomorphic curves that go into X. And I'm not sure if there's a rigorous definition of that. I'm not sure the status of that. But this theory sort of has the same properties, and you would expect that if there is a rigorous definition of linearized contact homology, then it will be isomorphic to this. But you can use, so this one, the definition's more complicated, but you can use it to get the applications you would want from linearized contact homology. So that's a nice application of this approach. Now, can you pass this down?
How do we compare this directly with the finite dimensional picture? So the base will be BS1, but it's not exactly that picture over there. It's with the loop space, right?
Right, so you should imagine the analogy is that M is the space of parametrized loops.
Mm-hmm.
And
Okay,
S1 acts by loop
Okay,
parameterization.
thank you. Thank you.
Actually, I have another question. So what if you instead thought of sort of CP infinity minus infinity as the base? So instead of taking your Morse function to be strictly positive, let it go to plus and minus infinity.
Yeah, so there's, if you think people do stuff like that, I'm not an expert on this, but there's something called Rabinowitz Floer homology. I think that's what you're asking about. So you have things going to plus infinity and minus infinity. All right, so I'm supposed to say something about gauge theory, which I haven't yet. So let's do that. So suppose now we have a family of 3 manifolds. So if this was too much notation with symplectic homology, just forget that ever happened. Okay, so now we have a family of 3 manifolds. So this will be a smooth fiber bundle where the fiber is a closed 3 manifold. So for any closed 3 manifold, we have various kinds of gauge theory. I'll be interested in either Seiberg-Witten/monopole Floer homology or embedded contact homology. So if for example, if we also had a family of, to put me more in my comfort zone, I might want a family of contact forms on the fibers. So ECH of a three-manifold with a contact form is the homology the chain complex, which is generated by certain finite sets of Rabe orbits. And whose differential counts certain J-holomorphic curves, which are mostly embedded in R cross Y. And Taubes proved that this embedded contact homology is isomorphic to one of the versions of monopole Floer homology as defined in Kronheim and Ruff's book. And the proof involves taking the Sabry-Witten equations and perturbing them using a large multiple of the contact form, and then the generators end up converging to these finite sets of Rabe orbits, and the Sabry-Witten solutions counted by the differential end up converging in a certain sense to holomorphic curves. Okay. So we can do that for a single three-manifold. Then the question is, can we do something for a family of three manifolds? So I would conjecture. So I think the question is not so much whether this is true, but whether it's worth proving. But the conjecture would be that and maybe somebody's already done this. I tried to search in the literature and I couldn't find it, but I'm not an expert. So one can define a family version of ECH as in the previous construction. So we choose a Morse function on the base as before. And then a generator of the chain complex would be a pair x alpha, where x is a critical point of FB, and alpha is an ECH generator, so this is some set of Rabe orbits on the fiber, pi inverse of x. We call this map pi. That map is pi. And then the differential, well, you have a vertical differential, which is just the usual ECH differential, and then the additional parts of the differential would be pairs of, you have a flow line of FB, and you have a solution of a parametrized holomorphic curve equation on the over it. And then this would be isomorphic to some kind of family version of monopole Floer homology. And one can maybe also define a family version of monopole Floer homology directly. I'm not sure what that may have already been done somewhere. I'm not sure the status of the literature on this.
Igor says that he thinks for the CP negative infinity base, you might get a Tate version of the S1 equivariant symplectic homology. He says there's some papers about this and related notions in the symplectic.
Yeah, okay, cool. Yeah, I'll have to look at those after. So, yeah, so I think one could make an invariant like this out of families of 3 manifolds. I'm not sure what sort of topological questions you might be able to answer with this. And also, if you have a family of cobordisms, then you should get some sort of cobordism map between these family Floer homologies.
Michael, so this also would work if you had a group action on your 3 manifold to give you an equivariant story, yeah.
Yeah, I think so. Yeah. Yeah, so if anybody knows relevant literature about this question, maybe they can tell me later. So there is at least one thing one can maybe do with this. So in the last couple minutes, or 10 minutes, I'll quote a neat result, which, well, with a little shoehorning, it fits into this framework. So this is about families of symplectic embeddings. So in symplectic geometry, people look at, you have X and X prime are 2n dimensional. So I guess I shouldn't give notation for the symplectic forms. Or 2-dimensional symplectic manifolds with boundary. And a symplectic embedding is a smooth embedding phi from X to X prime such that the pullback of omega prime is omega. So people have spent a lot of time studying these, starting with Gromov's non-squeezing theorem, which tells you when a ball can be symplectically embedded into a cylinder. So the basic example that I'll talk about here is where X and X prime are ellipsoids in R4. So if A and B are positive numbers, to find the ellipsoid EAB to be the set of Z in C2 such that pi times the absolute value of C1 squared over A plus pi times the absolute value of Z2 squared over B is less than or equal to 1. With the restriction of the standard symplectic form on R4. So you can ask, when is one of these embed into another? So there's a theorem by McDuff which says that there exists a symplectic embedding from EAB into ECD if and only if CK of EAB is less than or equal to CK of ECD, where where CK denotes the kth ECH capacity. And this is for all K. So the CK of EAB is the kth entry in the sequence AM plus BN, where M and N are non-negative integers, index starting at 0, in increasing order with repetitions. So you just look at all non-negative linear integer combinations of A and B, you write them in order, and the kth entry is the kth ECH capacity. It is also, that's the combinatorial formula for it. It has a definition in terms of ECH. Basically, for the three-sphere, like the boundary of the ellipsoid, the ECH has one generator in every non-negative even integer degree. And the kth ECH capacity basically says, how much symplectic action do I need to represent the degree 2k generator of ECH? And then the criterion for the embedding to exist, I guess I should say you need the open ellipsoid in the domain. And this criterion says these capacities are less than or equal for all k. If you want to actually check if that's true for all k, it's a little complicated. And there's some intricate combinatorial patterns that various people have worked out. For now, we just need to know the first two. So if A is less than B, then C1 of EAB is A, and C2 of EAB is the minimum of 2A and B. Okay. So now here's a cool theorem. So this was proved in my student Mihai Montano's PhD thesis. And there's a generalization which is a joint work with him and Julian Chides. So I really like this theorem. So here's the setup. I guess I should have shown you before how I like to draw these pictures. So you can draw an ellipsoid, you can project it into the plane where the first coordinate is projected into the absolute value of z1 squared times pi, and the second is projected into the absolute value of z2 squared times pi. And the ellipsoid EAB just looks like a triangle here. So I like drawing these toric pictures a lot. Anyhow, so we have an ellipsoid EAB and another ellipsoid ECD. So I assume that A is less than B and C is less than D. So that's just, convention. And for this embedding for one to be a subset of the other, I need that A is less than C and B is less than D. And finally, I have a slightly suggestive condition, which is I want that C2 of EAB, so that's this minimum of 2A and B, is bigger than C1 of EUCD. which is just C. That can happen. So those are the assumptions. And consider the loop phi from 0, 1 to SP4 is actually going to map to U2. So phi of t is e to the 4 pi it 0 if t is less than or equal to half, and 0 e to the minus 4 pi it if t is bigger than or equal to a half. So this loop, it first rotates the first coordinate by 2 pi, and then it rotates the second coordinate by minus 2 pi. So this loop is contractible in SP4 because the first half of the loop is conjugate to the inverse of the second half of the loop.
Yeah, one.
Sorry?
One on the diagram.
Yeah. I must be jet lagged or something for my last trip a couple months ago. The other entries are 0. So the theorem statement is that the loop of symplectic embeddings so that's the statement of this theorem right there. Loop of symplectic embeddings phi of t from E of AB to E of CD is not contractible in the space of symplectic embeddings from E of AB to ECD. Now this loop of symplectic embeddings, the image actually, every element of the loop, the image is the same. And this loop is contractible. If you're looking at embeddings of EAB into all of R4, this loop is contractible because it's contractible in SP4. But inside E of CD, there's not enough room to do the contraction. I think that's kind of cool. And it's proved basically, well, morally speaking, the proof is some kind of parameterized ECH, although the actual proof is very concrete. You don't need to say all of that. So you might be able to prove more stuff like this with various parameterized contact homology. I'm out of time. Thank you.